A confirmation about the audio, please, guys. If the audio is clear and available. Thank you. Wishing you all a very happy new year. I hope that the year is as fruitful as you dream it to be. And I hope in this new year you get that perseverance, that dedication and determination right. And you strive towards achieving your dream and your goal, whatever that goal might be. I hope you make some progress in that. So, with that, all the good wishes for this particular new year. Today is my okay. Simran, happy birthday. Again, the same wishes. Geo question was very tricky in the test. Okay. Were all the questions that tricky, or did you find some questions to be easier as well? See, it was the questions were the ones which you would spend some time. If you could spend some time on each of the questions, analyze it now. If you could spend some time with each of the questions, follow your basic logic, you would have got more of them correct. So try it again. Okay. You will have a separate analysis session of the questions. So maybe by tomorrow evening or day after tomorrow, it will be made available to you about the detailed analysis of all the questions. Okay. No issues if you didn't score very well. No issues. As long as you are learning where you are going wrong. Not when I say learning where you are going wrong, I don't want you to say that, okay, in this question I went wrong. No. What is the pattern of you committing your mistakes? There would be certain types of wordings, there would be certain types of option choosing that you are doing it incorrectly, even in polity, even in economy, even in geography. So identify that pattern. Okay. So, hello, a very warm good evening to all of you, and welcome to Baiju's Exam Prepares. Welcome to another session of climatology. Now, here, till the last weekend, we have been discussing about the portion of climate. And the basics of climatology is what we have been discussing, where we had discussed about the temperature distribution across the planet. We had discussed about the concept of urban heat island. We had discussed about isotherms and isothermal variations as they are experienced across the globe during different seasons. So that is basically few of the patterns that we had discussed. We had also discussed about temperature inversion. What do we mean by inversion of temperature? So when we say a temperature inversion, in that case, what we actually mean by saying that is the fact that at the lower level of the air, there is colder air which is trapped closer to the ground surface, and above it you have a layer of the warm air. So that is when the conditions they end up exhibiting a kind of a negative lapse rate. And that negative lapse rate as it is experienced, that is the condition of temperature inversion. Because under normal conditions, you observe a positive lapse rate. Warmer air at the bottom, colder air at top. Now, when you have a condition of a positive lapse rate, always the warm air being the lighter one will tend to rise up. Colder air from above being the heavier one will tend to sink down. So there will be consistently a vertical mixture and a vertical movement of air which shall be observed. But then when let's suppose you move forward or when you come to the portion of a temperature inversion, you are talking about colder air near the ground surface, warmer air above. So in these conditions, you don't experience that mixing of air. But why is it that colder air is there near the ground surface? Due to the region, due to the temperature, due to the climate, due to the movement of air. There can be multiple factors due to which this temperature inversion condition can be created. We have discussed two types of inversion. One is what we refer to as the surface inversion. Surface inversion that we saw was basically because of the fact that the surface suddenly cooled down during winter nights. And when the ground surfaces, they would lose temperature quite significantly, and to an extraordinary level, they would cool down. That is when the air in contact with the surface would eventually become colder as compared to the air above, because the ground surface has lost all its heat, all its temperature. So it is because of that phenomena that you will observe an inversion condition, and that is because of the sudden and a drastic cooling of the surface. That is what is surface inversion. Then you have what we refer to as the case of the subsidence inversion. Subsidence inversion, we have seen, is the fact that in higher latitudes, in mid to high latitudes, that too during the winter nights, you have the condition of a sinking air column. Right. Sometimes, let's suppose if you have a condition of a sinking air column, not always, not all the places, not through and through, but sometimes you can have the fact that in those areas of higher latitude, if you have a sinking air column, closer to the ground surface, because the ground is cold, the air is already colder. Now, that sinking air column will compress itself because it is falling down, and it will warm up. Now, it might happen that the air above might be at a temperature of minus 20 degrees Celsius. So by the time that it is sinking, it might not warm up enough. It might still remain colder. Then you don't have any condition of inversion. But sometimes it can happen that as it is sinking down, it warms up, and thereby its temperature increases in comparison with the lower air temperature. That is again an inversion. And that is what we refer to as the subsidence inversion. There are a couple of more inversion conditions that we will discuss, and then we will be moving into the portion of atmospheric pressure. So here, when we talk about the other conditions of inversion, we will talk about the case of frontal inversion. Okay, how many of us have managed to, I understand that it was a break, so how many of us have managed to put forward a revision? 3 days. Anybody who has revised the portions covered previously? Very good. The expected names are there. That is very important and very nice to see. Good. Okay. Fair enough. So hopefully now that we proceed into the depths of climatology, this week, if you have revised the previous portions and if you just simply carry on revising on a daily basis, then this week should be pretty much easier to take in as well. We will be spending time in climatology, guys. For that, we will be needing an extra session, a couple of extra sessions. We will make up for it on Saturday and Sunday in the mornings if possible, but we will take it as easy as possible because I want you to understand this with utmost clarity. Okay, because even in the prelims test series, you would have seen that the questions that are asked are not directly taken up from some. A few of the questions have been made easy, they are directly picked up, but conceptual clarity is required. Now, frontal inversion. What is frontal inversion? Now, for that, we need to understand what is a front. Now, we will discuss in detail about fronts and air masses after a couple of modules. But till then, just have that transitory understanding about what is a front. So, a front is a zone of transition. It is a zone of transition. Zone of transition of what? Of meeting of air masses. Of different temperature. So don't think about it that in my place, let's suppose wherever you are living, let's suppose Jaisalmer. So in Jaisalmer, I had hot air there, and from Bikaner, cold air came, and you had a front. No. Across the planet, as we will see in the immediate next module, you have consistent movement of winds in a certain direction throughout the year. You observe consistent and permanent movement of winds in a certain direction, what is also regarded as the permanent wind system. So let's suppose this is the planet. Now here, if this is the region of equator, consistently there will be permanent wind systems in this area. Up from around 30 degree to around 60 degree, the winds will move. And simultaneously, there will be winds coming from the polar region also, consistently. Why does it happen? We'll come to it in the next module. But there will be this consistent wind movement. Even in the southern hemisphere, you will observe this. A consistent wind movement across the planet, what are known as the planetary winds or the permanent wind systems. Now, as you can imagine, by taking a look at any of these winds for particular, which are also known by the name of westerlies, they are coming from the region of 30-degree north latitude to a region around 60-degree north latitude. So from 30-degree, it is carrying the air from around 30-degree, dragging it up till around 60-degree. So will it be a case of warm advection or will it be a case of cold advection? What do you think? If on the ground surface, they are bringing warm air from 30 degrees to around 60 degrees, that will be an example of warm advection. Very good. It is bringing warm air from 30 degrees to around 60 degrees north. So it will be a kind of a warm advection. Simultaneously, from the polar areas also, you have cold winds which are coming in. That will be the example of cold advection. Now, as they will come together, what will happen? There will be a zone of transition created in the entirety of area. In this entirety of the region, there will be a zone of transition which will get created. And that zone of transition, we will study later on again in detail, that is known as a front. Okay, so that is the zone of transition, which is a front. Now here, whenever a frontal formation is observed, there will be the different property of air masses. Cold air is always going to be heavier as well as denser. Cold air is always going to be heavier as well as significantly denser. Warm air is going to be lighter always, right? Why? Because in warm air, and listen to this very carefully, previous class also we had devoted a lot of time to understand that warm air is lighter. So again, a quick recap in the initial portion of the session itself. Cold air will have a lot of particles close to each other because there is a removal of heat energy. That is why the air is cold. So when there is a removal of energy, a lot of the particles with low energy will come closer to each other. That is why cold air is always heavier. Whereas warm air, because there is injection of energy, there is a high amount of energy going into the region of warm air. What does that mean? That basically will mean that there is a significant amount of movement amongst the particles. The particles, they tend to move quite significantly, quite rapidly. And as there is a significant amount of movement, the density will reduce. There, the particles won't be so very close to each other. So warm air is lighter, cold air is heavier. Now, under that premise, if you have the movement of winds, here, this is the cold air. And let's suppose you have another column of warm air. Warm air. Let's suppose the warm air and the cold air, they are moving towards each other. Let's suppose. Now what will happen? Will it happen like the good old family movies that you had, that everybody got together, they lived happily ever afterwards? No. Will it happen like in the cartoons that you see, that cold air, warm air, something blue, something red came together, orange color, moderate air is evolved at the end of it? No. We are talking about an air parcel or an air sample which has got homogeneity for thousands of kilometers. They have a uniform property for thousands of kilometers. So they will not readily mix with each other. And as they are being pushed towards each other, eventually, the cold air being the heavier one will stick closer to the surface. The warm air being the lighter one will simply climb above. The warm air here, it will start to climb up. The cold air will serve as an incline, and some part of the cold air will also be dragged by the warm air upwards, but mostly the warm air being the lighter one, that warm air will start rising up. And that is when you will come across a scenario where this warm air would have eventually climbed on top of this. You would have a warm air that would have climbed on top of this. So that is when, if you consider the lapse rate in this area, in this particular zone, if you consider the lapse rate, what will be the lapse rate? Positive or negative? Here. Very good. Here it will be a negative lapse rate because the cold air is closer to the ground. The warm air is the one which has ridden it upwards. So that is where this kind of inversion which is there, this is a temperature inversion. But temperature inversion has occurred. Why? Has it occurred because of sudden cooling of the surface? No. Has it occurred because of the sinking of air? No. It has occurred because of formation of a front. That is why this is what is regarded as frontal inversion. We will discuss the fronts in much greater detail about what these fronts are, where they are created, what are their types, what is the weather associated, which regions experience this, how these fronts lead to the cyclone formation. All of these we'll study in detail in a couple of sessions. Okay. So this inversion which is caused is because of the formation of a front. Okay. Now, after this, we come to another kind of inversion that you observe in the mountainous areas nearby, and that is the case of valley inversion. So what is this valley inversion? So basically, this is the temperature inversion which occurs during night times in the region of mountain valleys. Okay, so is this font size better, guys, or do you want a larger font size? Is this thickness okay, or do you want okay, don't worry, we'll switch it to the larger one. Okay, so observed in the valley bottoms, during winter nights. So what happens? Let us understand. Here, let's suppose this is the case of the mountain valley. Now we have seen that as you move higher up in altitude, even though the insolation is high, but because the air is so very less dense, air is so very rare high up in the mountains, that loss of heat is also very quick. So high up above the mountains, you have very low density air. right? Air of particularly and significantly low density. So here you will have colder air on top. Are we comfortable with this? That on top of the mountains during the night you will have cold air, because the warm air, the all the heat that was there, the mountain tops would have lost that very easily, because the air above it is very less dense. So colder air at top. Now at the valley bottom, in comparison, will there be a colder air or the warmer air? In comparison, the valley bottom will have colder air or warmer air? Warmer air, very good, because it is closer to the sea level. So here you will have a warm air layer. Now, if I ask you, out of A and B, which is going to be heavier? A or B? Which is going to be heavier? Always A. Very good. Always it will be A. Why? Because colder air is always heavier than warm air. Regardless of the density, the colder air will always be heavier in comparison to the warm air. If let's suppose we had been talking about 20 kilometers higher up as compared to the sea level, maybe there would have been a difference in weight. But here we are talking about the closer portions: mountain top, valley bottom. Mountain top you have colder air, valley bottom you have warmer air. So this will be the heavier one, this will be the more denser one, so this will start to sink. Maybe it will warm up a little bit, but still it will be so very cold that it will be colder than the valley air. Eventually, what will happen? It will displace. It will displace the air at the valley bottom. The warmer valley air will be raised up, will simply be pushed up. Whereas the colder air would now have replaced it and would have reached here. So this is an inversion. Imagine if the shape would not have been such that the cold air simply starts to sink down. Then this would have never happened. So here the inversion has occurred purely because of the attribute of the topography of the valley. If the valley formation would not have been there, there would not have been such kind of an inversion. So that is why this kind of a temperature inversion which occurs is known by the name of valley inversion. That is why in the thin and narrow valleys, where the valleys are very, very thin, very, very narrow, in the thin and narrow valleys, you experience that during the night times, the temperature suddenly drops. You will never observe. I'm talking about thin and narrow valleys. I'm not talking about a large valley like a Kashmir valley, etc. No, I'm talking about very thin and narrow. So that is why when you cross the mountains, you will observe that habitation, cities, etc., they are there, but they are there on the side of the mountains. They are never there at the bottom of the valleys. One of the fear that they always have in the valley bottom is that sudden substantial amount of flood. But the other problem is that during night time, the temperature dips quite significantly and very rapidly. Many of the plants eventually they can die as well because of the frost that occurs at the valley bottom. If you have a broader valley where the valley bottom in itself is many kilometers thick, then you will have different conditionalities of air mechanism. But in narrow valleys, the temperature suddenly drops. Now, however, if let's suppose you have a valley which is open from the end, that you have narrow mountains on the sides, but it is open at either ends so that the air can flow. through the valley, like a passage, the air can flow. In that case, you won't observe that valley inversion to occur, because then you will have the air drainage. The air can drain from one area to another, so the cold air won't be substantially accumulated only at the valley bottom. So that is why open valleys, you won't observe these drastic conditions. But in cases where you have the closed valleys, where you have narrow mountains closed from all sides, in such kind of valleys, the valley bottom will become very, very cold very suddenly. Okay, causes frost formation on the plants, death of the plants also. All these factors are created because of this. So that is the case of valley inversion. Okay, yes, in gorges also you'll observe this. Now, after this, have we taken up these questions for discussion? Have it? I don't think we have discussed these questions. No. Okay, let's take these questions up for discussion and then we will proceed ahead. So, normally, the temperature decreases with the increase in height from the Earth's surface because the atmosphere can be heated upwards only from the Earth's surface. There is more moisture in the upper atmosphere. The air is less dense in the upper atmosphere. Which of these factors are attributable for the decrease in temperature with height? Very good. Majority of you have given the incorrect answer. So we both should be proud of ourselves. So many of you have marked B. Okay. Let us concentrate on this option B. Many of you have marked this. So there is more moisture in the upper atmosphere as compared to the lower atmosphere. Can anybody explain this reason? Is there there is availability of more moisture in the upper atmosphere? Yes, Sushmita, please go ahead. I'm giving less time. Understandable, but does not mean you mark incorrect answer, my dear friend. Sushmita, I will wait for your reasoning. But till that point of time, let me make it very clear that the density of the atmosphere is maximum closest to the surface. Dust particles, water vapor, gases, their proportion will always keep on reducing as you keep on going higher up. Their proportion will always reduce. Okay, so the density of water vapor, dust particles, gases is always going to be maximum closest to the surface. Okay, so this is incorrect. Now, the first statement, atmosphere can be heated upwards only from the Earth's surface. Now, ideally, if you think about it in absolute entirety of the atmosphere, you will find that there will be contradictions that no atmosphere is heated by X-rays in the region of thermosphere. It is also heated by the ozone layer when you come to the mesosphere. But here we are talking about a case of positive lapse rate, which is experienced where? In the troposphere. Right? Whenever you see that normally the temperature decreases with the increase in height, you are talking about the region of troposphere. That is the premise established by the question itself. So then in the troposphere, where is that heat getting received from? It is the heating, the long wave radiation from the Earth's surface, which gets emitted by conduction. The ground surface heats up the air above. So that is what makes the first statement correct. Is that understood, Vibhu? You had a problem with that? Okay. Now, the second statement we have established is incorrect. The third statement, that air is less dense in the upper atmosphere, that is correct. Is that relevant to the answer? It is. Because with height, you don't have enough things to trap the moisture. If you had a significant density in the upper atmosphere, the not enough density to trap the heat, rather. If you had significant density of air in the upper atmosphere, they would have trapped the heat, retained the heat, maintained a higher temperature. But because air is very less dense, the temperature is lost very easily, and that is why the answer is C. And Sushmita, yes, if upper atmosphere have more moisture, if upper atmosphere have more moisture, then it absorbs heat remain itself. But it's not. That's why when we go upwards, we feel cold for due to heat loss for the expansion. So, Sushmita, what are we trying to prove here? That upper air has got less moisture or more moisture? Understand, always respect the elephant in the room, and that is gravity. Gravity will always pull anything having mass, having weight closer to itself. Yes, so then it is correct. Okay. Do we see steam in lakes in winter mornings? That is a steam fog, Anjan. We will discuss in the portion of humidity and precipitation. Then, the annual range of temperature in the interior of the continent, like Delhi, like Lucknow, Chandigarh, is high. The annual range of temperature, summer winter temperature difference, is high as compared to the coastal areas. What is or are the reasons? Why is it that there is a substantial range of temperature experienced here? Is there a thermal difference between land and water? Variation in altitude between the continents and oceans? Presence of strong winds in the interior? Heavy rains in the interior as compared to the coastline? Which of this factor is most apt for the temperature difference or the range of temperature difference between the summer and the winter months? Okay, should I have given more time here? How air is less denser in upper surface when temperature is low? Air is less dense because of the factor of gravity. Okay, Arjun. Even if the temperature is low, let's suppose due to some conditions near the ground surface, the temperature is low, still that will be, in comparison to the air in mesosphere, still it will be more denser. Okay, so the low density near the ground surface will still be more denser as compared to the upper air. I hope you are able to understand this. So here at least majority of you have given the correct answer. So there's a thermal difference between land and water which creates the moderation, movement of wind patterns, etc. Variation in altitude between the continents and ocean. Can that be a reason why Delhi experiences different temperature as compared to Mumbai? First of all, this statement in itself is incorrect. But can that be a reason why, for example, Delhi or Lucknow will experience a different temperature range as compared to Mumbai and Chennai? Obviously not. There, the moderation in temperature in the coastal areas is because of the frequent movement of the land and the sea breeze and the presence of moisture also. So this statement is also incorrect. Presence of strong winds in the interior. Coastal areas experience much stronger winds. Heavy rains in the interior as compared to the coastline. Coastlines will always experience more heavy winds occurring. So the correct answer is going to be A. Okay. Now, we move to the portion of atmospheric circulations. Inversions lead to which geographical phenomena? Inversions basically lead to the sudden lowering of temperature. In certain areas, it can lead to the lack of mixing of vertical mixing of air. In certain regions, it can cause frost near the ground surface, heavy amount of precipitation. By the time that we are done with the frontal inversion, you will be able to answer this question much more aptly. Okay. Leaderboard. Okay. We will discuss some of the more questions along the way. But if someone asks for a leaderboard, generally they would have got all of them correct. So this is the leaderboard. Good. Very good. So now we come to the portion of atmospheric circulations. Here we are going to study the factor about pressure. We are going to study about the wind movement. What are the factors which influence the movement of the wind? Then we are going to study about isobars, just like isotherms. We are going to study about the permanent wind system, the atmospheric circulation, the local wind system. That is what is going to be covered here. Here, basically, we have the portions for prelims. Basic factors influencing wind movement, then basics of permanent winds, and pressure belts, then after that basics of shift of pressure belts, or shift in, or rather than shift, onshore and offshore winds, then from local winds you get questions, or you can get questions, match the following kind of questions: region where they are expected to blow, and nature of the local winds, hot or cold. Okay, so these are the areas relevant for your prelims. For the mains examination, you have pressure belt systems, system, and tricellular model of circulation. See, this is a topic which shall be driven straight from the concepts that we have covered in the previous module. As simple as that. Heating, cooling, etc. I'm not going to spend much more time on that heating and cooling anymore, because we have spent considerable amount of time and lecture there. So this is going to follow straight away from those earlier portions. Having said that, we will study the portion of pressure, etc. from the basics. And once we understand this tricellular model of circulation, the movement of trade winds, westerlies, what are ITCZ, etc., that is going to form the basic framework which is going to help you understand about rainfall distribution in the world, Indian monsoon, jet streams, El Nino, La Nina, Indian Ocean dipole, then the global climatic distribution, why there is onset of monsoon, what is winter monsoon, what is summer monsoon. Every detail of climatology will be driven from this basic concept about where the winds move, what is the pattern or the direction of the wind movement. That is where the entire discussion will be driven from. So please ensure that you understand this to the last and the latest of the detail. Okay, so that is basically where this particular chapter might not have direct questions being asked that frequently in the exams. In prelims you get questions about westerly trade winds, for example, around 30 degrees or around 60 degrees north latitude, the eastern part of the continents will experience offshore or onshore winds. Such kinds of questions are always asked, but then majority of the utility of this tricellular model of circulation, the wind pattern, etc., will be required when you are talking, let's suppose, about the development of a cyclone, the movement of a cyclone in a certain direction. Tropical cyclones move from east to west, temperate cyclones move from west to east. All those later on details that you will come to will be driven from this portion itself. Okay, so that is why this portion becomes very, very important. I didn't understand the previous module. Beautiful. Which portion? The entirety of it, or were there certain snippets, etc.? The entirety of the previous module, if it is not understood, then I can't do much now. But I have taken these modules very, very slowly, and each of the questions have been addressed. So either it was not even understood to ask a question there, which is the portion that you have not understood. Stratosphere is warmer than troposphere. What type of inversion is this? This is a kind of a permanent thermal inversion, what is referred to as the upper air thermal inversion. So even in upper atmosphere, Muskan, that is upper troposphere, there are two types of inversion if you refer to it. One is the upper air thermal inversion, where beyond the troposphere you have the warmer stratosphere. The second is upper air mechanical inversion. That mechanical inversion is what we have studied in the form of subsidence inversion. Okay. Sushmit, why variation in altitude between continents and oceans is not correct? Variation in alt. Okay. So read the question carefully, my dear friend. What was the question? That is where understanding, see, always understand one thing. One of the key points of even writing answers and getting questions in prelims correctly is answer what is asked in the question, not what you know about the question. What is asked? So, what has been asked here? The annual range of temperature in the interior of the continent is high as compared to the coastal areas. What does that mean? It implies that the range of temperature in Delhi, Lucknow, Patna, etc., is high. Now, why is that the case? Is that because these are situated at an elevation as compared to the water body? Is that the reason why Delhi becomes around 48 degrees Celsius in summer? Is that because it is situated at an elevation to the water body? Absolutely not. That is why here, if you take a look at Patna, it is almost situated at the same level as compared to the Bay of Bengal, almost situated at the sea level. Right. So it is not the reason why should be a greater variation or a greater range in temperature. Why is there a greater variation or a range in the coastal areas such as Mumbai, Kolkata, Chennai? In all these areas in the coastline, temperature is consistent throughout the year. There is no variation between summer and winter temperature. Is that because of the factor of altitude? If that would have been the case, Varkala, which is situated at a slightly greater altitude compared to the coastal area, compared to the sea level, they would have experienced extremity of temperature. But that is not the case. So the moderation of temperature in the coastal area is not because of the variation in altitude. It is because of the movement of winds from the sea. It is because of the presence of water vapor that retains the heat, that maintains the temperature. Altitude can never be a factor. Is that understood? Okay. Lakshmi, we will discuss the mains questions also. Don't worry. GIB, for that, I would recommend kindly go through because you have attended the sessions. Maybe you were unable to look at the larger picture. I would urge you that before tomorrow's class, kindly look at the recordings of the module 6 once again. That recording will be very, very beneficial once you have attended it. Now, because you have understood, maybe you would have approached each of them separately. Now try to take a larger picture altogether. You can put it at a faster rate and a faster speed. You can hear it up. It will be automatically clearer. Shelga, don't worry, it will happen. This is the first test that you have given. What was your expectation that in the first test, how much should you have scored? What was your expectation? So please have patience. It will come. The marks will come. Again, I will what I have been repeating continuously for the past 3 to 4 classes. Analyze where you have done the mistakes, why you have done the mistakes. Analyze that. Why you have done the mistakes. And then you will improve. Okay? Right? And now we come to the portion of atmospheric circulation. Here we have the portion of atmospheric pressure that needs to be understood. What is pressure? One kind of a pressure is the pressure of timeline that many of you are experiencing. Exams are approaching fast and you have to finish the portion. So that is one pressure. But here clearly we are not going to talk about that. We are talking about some different pressure altogether. Pressure, in pure scientific terms, is force applied per unit area. That is pressure. But in normal layman's term, if we talk about it, what is pressure? So let's suppose I have this particular remote with me. Let's suppose. Now this imposes a weight on the surface. This ends up imposing a kind of a weight on the surface. So can we say that the surface experiences pressure? We can say that the surface experiences pressure. So this is a kind of pressure which is exerted, isn't it? So that is basically the weight imposed on the surface. Now, when we say atmospheric pressure, what is that? So the pressure imposed by the atmosphere over the ground surface. Let's suppose we consider a column of atmosphere here. So the pressure imposed on the ground surface. That is atmospheric pressure. Now, let's suppose I consider a warm air column. Let's suppose. Warm air column, ideally, particles will be a bit far away from each other. Ideally, particles will be a bit far away from each other in the case of warm air column. Right? Now, let's suppose I also consider a cold air column. Now, in the colder air, we do know that the particles will be much more closer to each other. The intricacies of it will be different. The cold air column will have a different volume altogether. All those details I will take you to the next level slowly. But as of now, let's be comfortable with the basic terms here. Okay. So here, a region which has cold air above it, you compare it to a region which has warm air above it. Now, if I ask you, out of this place A and the place B, which will experience a high pressure, A or B? Why A? Lakshmi, Anushka, and a few of you else, Devyani. Why A? It will flow easily. So then what will happen? If they flow easily, then what is pressure? Pressure is the total weight which is imposed, right? So here, basically, if you observe these particles, there are lesser number of particles, so they will impose lesser amount of weight. Here you have greater number of particles, so they will impose greater amount of weight closer to the ground surface. So B will indicate higher pressure. It will always be in comparison to something. It will indicate a case of a higher pressure. Now, here, by this, we can come to a very simplistic conclusion that the regions of warm air will generally indicate a low pressure. The regions of cold air will generally indicate a high pressure. Are we comfortable with this assumption? That the regions of warm air, there you will generally have a lower pressure because of lesser particles in the air column above it. The regions of cold temperature or lower temperature will generally be associated with higher pressure. We are comfortable with this? Okay. Having said that, let me also tell you that temperature is not always the main factor which will influence the pressure. Pressure, in fact, can be independent of temperature. Okay. But before that, let me have the first conclusion. First is the thermal influence on pressure. We do know that warm air is lighter, cold air is always heavier because of the particle density. So here, whenever you have regions of cold air, have a higher pressure, as compared to regions of warmer air. Let me also attach a caveat here. This is not true for all cases. Pressure is also influenced by wind movement. Okay, so pressure is also influenced by the wind movement. So that is where thermal factor is one of the factors which can determine whether the pressure is high or low, and that is basically because the thermal influence here We do know that warmer air will have lesser particles, less density, colder air will have greater density. So there will be a sinking air in general, and that will cause more pressure. Now we take a look at the definition. So, what is atmospheric pressure? Atmospheric pressure is basically the weight of the column of air contained in a unit area from the mean sea level to the top, and that is called as the atmospheric pressure. In simple terms, the weight imposed by the air masses or the air parcels on the ground surface on any region is known as atmospheric pressure. So, with this particular logic, if I tell you to compare between two areas, one is a high mountain at a height of 8 kilometers from the sea level, another is the sea level, let's suppose, the plains. Now, here, out of A and B, which will have lower pressure? Which will have lower amount of pressure out of A and B? Good. Here, now we are thoroughly confused. Apply simple logic. Don't get waywarded by the various different doubts and the second thoughts, applied logics that you are developing. Simple logic here. Density of air reduces with height. Is that a reality? Yes. So, in this particular portion, between the mountain top to the sea level, can we assume there will be very dense particles in this area? So, the atmospheric pressure at A, whatever it might be, it will be an add-on to this extra air, which above B you don't have that extra air. Above A, you have this extra portion. Isn't it? So that is why always mountain tops will have a kind of a low pressure. Always. The mountain tops, etc., they will always indicate a substantially lower amount of pressure. Pressure decreases with the increase in altitude. Remember that. Pressure decreases with an increase in altitude. That is why when you go higher up, you suffer from altitude sickness. That is why it is always advisable that if you are doing, let's suppose, a mountaineering expedition, it is not as if people cannot climb multiple different heights in the same day, but they don't do it. They move from one base camp to another, they take rest the whole day so that their body acclimatizes to the low pressure. That is why suddenly when you move up in an aircraft, many of you would have, generally those of you who have had the problem of, let's suppose, sinusitis, your sinus glands swell up, or you have runny nose and those kind of things. Or if you observe that your family, your relatives, or even if you, let's suppose, are suffering from an issue of blood pressure, flying in the airplanes become very difficult and very painful because the outside pressure reduces with height and your inside body pressure is so very high, it appears as if things are pushing out. That is why you will find that oftentimes while going for trek in the mountains or sudden such increase in altitude, people start to bleed. The blood starts pouring out from the ears, from the eyes, blood starts to come out because the internal pressure is so high, outside pressure is less, everything wants to explode. right? That is why it is always advised to acclimatize. For example, it is never advised to take an aircraft directly from Delhi, land into Leh Ladakh, and go up in the mountains in the same day. Always advised that spend one day in the lower altitude so that your body acclimatizes to that low pressure, low oxygen level. Okay, I hope that is understood. Okay. Right now, don't think about proportional or inversely proportional. Keep yourself free from those foundations as of now. We will see later on that how each of them, they are individually determined by many factors. For example, we will also see how regions, previously we had seen in this particular slide, that in the previous slide, that warmer regions have low pressure. We will see in a couple of slides that certain warm regions are also zones of high pressure. So it is not always a black and white scenario. Keep your mind free of all the prejudices. That does that mean it is proportional with altitude? Does that mean it is inversely proportional to temp? No. Let it be. Let it, wherever it is, let it be. The final linkage, I know you want to have that conclusion so that you can write it down, you can rectify it. Don't do it. Leave it. We do know that temperature is one of the factor which can influence pressure. Altitude is another factor which can influence pressure. Are we comfortable up till this point? Lakshmi, at the time of cooking, warm liquid try to flow out of the utensil. In this case, the same pressure phenomena happen, or is it the different phenomena? That is the same phenomena. That is the same phenomena, Lakshmi, because observe in the case of when you put something on a pressure cooker. Now, if you, let's suppose you convert it, you pour some water to it, water will change into steam. That steam will try to come out. That is how the materials get cooked. If, let's suppose, you don't pour in water, you simply keep the vegetables or whatever you have to cook in the pressure cooker, you simply keep it there and close the lid. Regardless of how much you heat it, it will burn, but it won't basically release that pressure because you don't have that gas. It is, pressure cooker is the ideal example that I have given to you as well. I always use that as an example for volcanic eruptions, that how water can get converted into gas and then add on to the eruption. But this is not always the ideal analogy to the pressure cooker, but if you want to understand it, fair enough. Sir, you said warm air has two, has low pressure and cold high pressure. But now you said with increasing altitude, it decreases too much. That is why I told you. In the previous slide, also, Prem, I had told you, understand, this is not true for all the cases. Pressure is influenced by other factors also. Temperature is one of the factors which influences pressure. For example, solar heating. I tell you that solar heating leads to high increase in temperature. But then I tell you ocean currents also influence temperature. So in the coastal areas of cold current, you have, despite being near the equator, they have they have low temperature. So it is not only one factor which controlled temperature, is it? Temperature earlier that we have studied was controlled by many factors. Similarly, pressure is not, it is not a one golden rule that you study that, okay, warm air, low pressure, cold air, high pressure, I will rectify it. No. That is why I told you, keep yourself free from the foundations. Why is it that at a higher altitude, low pressure is there? Is that understood or is that not understood, Prem? Is that understood? Why anybody having difficulty in understanding why at higher altitude the pressure is less? No? Everybody has understood it? Okay. Let me write it down. Because density of air particles decreases with altitude. Altitude. Hence, places of higher altitude will experience less air. Means they will impose less pressure. Means pressure is lower on top of mountains. That is why in airplanes also, okay, in airplanes also you would have observed that pressurization cabin, etc. But is that understood, Kaushik? Can gravity be the other reason? What other reason? This is the only reason. The only reason for entirety of the thing is gravity. See, I don't want to write the same thing in every class. Because of gravity, that is why I say please revise. Gravity, maximum air particles. See, if we keep on going at this pace, I'm okay with going slow, but if we keep on going at this pace, then it will be very tough, guys. Are closer to the ground surface. Is that understood now? Okay. So, atmospheric pressure is basically the pressure exerted by the air on the ground surface. That is what is known as the atmospheric pressure. Okay. Now, here it is expressed in the terms or the units of millibar, and the average pressure, the normal average pressure at sea level is expected to be 1013.2 millibar. A pressure which is higher than 1013 is expected to be or is referred to as a high pressure. A pressure which is lower than 1013 is said to be that of a low pressure. Okay, but that is the case of variation in pressure. Now, about the winds and the air circulation. So, before that, actually, now I am a bit scared from the time that you have talked about can gravity be one of the factors? So, about rise and sink of air. Do we know that warm air is lighter? Warmer air is lighter. Why? Why is it the case that warm air is lighter? Because when the air is warm, that means the air has got energy. That means the earlier, let's suppose these particles were present. Let's suppose these particles were present in the air. Here, now, if the air is warm, each of these particles will have their own respective movements. Each of them will be having their own respective movements. Now, as they are moving, why are they moving? Why will the particles move? Because they have energy. Energy is provided due to heat here. So, as they have energy, it might always be possible that some particles will escape the system as compared to normal scenario. So, in comparison, you will have lesser number of particles. So, warm air becomes lighter because of this phenomena. Due to higher energy, due to higher amount of energy, particles move away, making the air sample lighter. The air becoming lighter than the surrounding rises up. Okay, but till when will it rise up? Till when will this air rise up? There would be a limit. It is not the case that air will rise up, will stop only in the region of the sun, isn't it? So why is it that basically the till where will this air rise up? Up to gravity. Okay, so gravity will decide. So what will be the final decision of it? Okay, in simple terms, this will rise up till it is warmer than the surrounding. Till it is warmer than the surroundings, till that point of time, it will continue to rise up. Because when we say it is warmer than the surrounding, means the surrounding air in comparison is colder, is slightly heavier. So this one lighter one will continue to rise up. It reaches here. Still, it is warmer than the surroundings, means more energy, means the particles will keep on having that energy escaping that system. So it will continue to becoming lighter. It will continue to rise up. Eventually, it will reach a position where the surrounding temperature may be as the temperature of this particular air, because as it is rising up, it is cooling along the way. It is not as if a 30 degree Celsius temperature air, if it has started rising from the ground surface, even at a height of 2 kilometers or 5 kilometers, it will be 30 degrees. No, it would have cooled down. So it is cooling along the way. But despite that, it might still be warmer than the surrounding colder air. It will come to a situation where its temperature is equivalent to the surrounding air. Then it won't rise any further. Of it, or if let's suppose if it comes to a situation up to the region of tropopause, beyond the tropopause, stratosphere is warmer. So there you already have some lighter air. So it won't rise up in that region because it has cooled down. So as long as it is warmer than the surrounding, that means it has got greater energy as compared to the surrounding. It will continue to rise up. So the air rises up as long as they are warmer than the surroundings. Comfortable with this? Now, we know that cold air is heavier and denser. Why? A couple of you have the habit, despite of what is being explained, you have a question, you keep on copy pasting that question, regardless of the fact if whether your question is being answered in the explanation, you keep on copy pasting those. That is why I will tell you, please listen to. It need not be the case that I take your name and then only I will answer your question. Listen to the explanation. Many things become automatically clearer. For example, Twisha, by the time that you have pasted this question of yours, you have pasted this at least 5 to 7 times. I have explained it, the answer to your question, in the meanwhile twice. But continuous copy paste is happening. So your question is, sorry, but how some particles move away? That is what I have been repeating myself. Listen to this carefully before you copy paste it again. Listen to this very carefully. Why is it that the particles in the warm air will move away? Why is it that the particles in warm air will at all, if they at all have a movement? Why? Because of the fact that when we say warm air, what do we mean by warm air? We mean higher heat energy. Heat, heat is an indication of temperature or energy. When you provide that heat energy, the particles will get excited, they will have more energy. So when they will have more energy, they will start moving from one place to another. They will significantly start moving. As they start to move, they will escape the system. Let's suppose I have a parcel of air of half a meter cube, 1 meter cube, 2 meter cube. If I warm it up, many of the particles with the energy that they have, they will escape that boundary of that system that is getting heated up. So eventually, what will you have? The air parcel with lesser number of particles as compared to earlier, because many particles have escaped. Why have they escaped? Because of that heat energy which is provided, which has provided the energy, kinetic energy to the particles so that they can move. And that is why the air becomes lighter and tends to rise up. Is that understood now? Now you'll go silent. And GIB, your question. Again, that you have basically repeated at least 7 to 8 times. Why cold air will gain density? Why colder air will gain density? Can we have some patience? We are coming to that. Okay? Okay. So cold air is heavier and denser in comparison. We have discussed all of this in the previous class also. So it gives me immense amount of joy to understand that we have not understood things in the previous class. So that is very, very joyful to say the least. So cold air is heavier and denser. Why? So when we have any air which is cold, can we say that energy has been extracted from the system? Colder air means less heat. We can talk about colder air as saying less heat. So in a way, can we say in this case, heat has been, heat energy removal will cool down the air? Are we comfortable with this assumption that cooling of air can be said to be the removal of heat energy? Fair enough. Removal of energy, can that basically mean that you have particles have less energy in comparison? Can we have that? Each of the particles will have their own gravitational pull. They will try to attract the other, but then that attraction is defied because of the energy that these particles have. They continue to move in random motion. But if you extract that energy out, if you remove the energy out of the particles, means what? They will get attracted by the other particles. They will, in a way, clump together because they don't have energy to move. So they will start clumping and falling with respect to each other, accumulating with respect to each other. Very less movement of particles. Is that understood? Very less movement of particles. When you have very less movement of particles, that basically means they, yes, Ashish, that is correct, start clumping or accumulating together. Can we have that? So if we have earlier, let's suppose the particles were placed here, 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 randomly they were placed here. Now, if you extract energy out of them, all these particles, they will start clumping together. All these particles, they will start clumping together with each other. The intermolecular forces of attraction will be the most dominant one, right? Rather than the energy given. So here, what do you find? You find that the air density or the density of air particles, density refers to the closeness with which the particles are packed. So that is why here we will have a greater density of particles attached. Are we comfortable with this now? This is the second time that we are discussing the same issue. In fact, it is the third time if you deliberate upon it. Fair enough? Now, because this is heavier, what will happen? As the air is colder, it is less energetic as compared to the air around it. So this air is now colder than the surrounding, means more particles would have clumped here. So these particles would make this particular portion heavier and the cold air starts to sink. Okay, that is where cold air will start to sink. But up till what point? Till when will it sink? Will start to sink. As long as it is colder than the surrounding, it will sink. As long as it is colder than surrounding. As long as it is colder than the surrounding, it will continue to sink. Now, you have two conditions, thermal conditions that we have seen. One of the condition is basically near the ground surface. Let's suppose you have a region which gets heated up. No, Prem, you cannot say that. You have a region which gets heated up. And you have a region which is colder. Let's suppose the region of the poles. Now the warmer area, the region which is very, very warm, there the air above this warmer surface will also get heated up. This is a pure application of what we have studied in the previous slide. This is no rocket science that I'm telling you. Okay. So this is just the derivation of things that we have discussed in the previous slide. If you were comfortable there, there's no reason why you should not understand this. So here, this particular air parcel, by virtue of being in contact with the warmer ground surface, will also become warmer. Air becomes warm. I will write it down. Air becomes warm. Becomes lighter. As a consequence of that, it rises up. So it will rise up. As it rises up, the air becomes cooler and colder. But as long as it is warmer than the surrounding, it will continue to rise up. In most of the cases, the air will rise only up till the region of tropopause, not beyond that. Why? Because beyond tropopause, you have the stratosphere, where you already have warmer air in the surrounding. By the time that this air will reach the region to the top of troposphere, its temperature would have dropped to minus 60, minus 50 degrees Celsius. So clearly it will be colder than the surrounding air of stratosphere. So colder air does not rise. So that is why it will not rise in the stratosphere. So majority of the circulations happen in the troposphere itself. Now, it has reached the region of tropopause, but it cannot rise any further. So what does it do? So this air, eventually after this, it is not the case that one bubble of air had come and then there is no such further movement of air. The ground surface is continuously getting heated up. So another parcel of air starts rising up closer from the surface as the earlier one was rising. Another parcel also became hotter and it also started rising up. Meanwhile, another portion from the ground surface has also started rising up. So you will have a continuous upward movement of air. But the air cannot move through the tropopause, cannot move into stratosphere. So where will the air go? It is continuously rising up from the ground surface and then it is hitting the tropopause. It cannot rise above. Where will it go? It will diverge. It will move in different direction. It will diverge. Right. There will be divergence here. It cannot sink down in the same area, can it? Because in the same area, you have consistent rising air. So it cannot sink there. So even if it has to sink somewhere. Right? Meanwhile, let's shift the attention to the region of colder ground surface, maybe near the polar area, let's suppose. Now here, you have near the ground surface, the temperature will be very, very low, very, very cold condition. Here. So what will happen to this air parcel? It will become very heavy, it will sink. Now, as this air has sunk, it creates a gap above it. So the air parcel which was above it will also sink to fill that gap. That has created a gap above. Now the air parcel above it will sink to fulfill that gap. Like that, air has got a sinking portion. Air has got a sinking portion. There will be vacancy created here. Can we think about it? Because the air is sinking here in the top of the troposphere. Can we think about a vacancy of air particles created here? We can think about it. Meanwhile, in this region, You have a surplus of air particle, more of them rising up from the ground surface. So in a way, you have a surplus of air particles, and here you have a vacancy. So the air will move in as it is moving to the region of top of tropopause. In the region of top of troposphere, its temperature is consistently around -50, -40. So it is cooling down. The air has cooled down sufficiently. By the time it reaches here, this will also start to sink. Near the ground surface, a similar phenomena plays out. As the particles here are sinking, can we say that in the colder region, there will be surplus amount of atmospheric particles here? Because the air is sinking, can we say there will be surplus amount of atmospheric particles in this area? Comfortable with that? Yes. Now here, as the air is rising in the warmer region, can we say that as the air has risen up, there will be slight vacancy created at the bottom? We can say that, isn't it? That there will be a slight vacancy created at the bottom. So in one place you have a surplus, in one place you have a kind of a vacancy. So the particles, the air particles, will rush in to fulfill that vacancy. So from the region of surplus to a region of deficiency, the air will rush in. This movement of air, any horizontal, upward, any kind of movement of air, that is what is regarded with the name of wind. This is what we experience in our day-to-day lives. When we experience the wind movement, this is what we actually end up experiencing. Okay, so that is the wind movement. Now, here you have seen a complete circulation of air, but circulation induced by temperature conditions. That is, this region has been warmed up, this region has cooled down. That is why you have this circulation. Now, in this area, what will be the pressure in this particular region? The air is rising up. The air is rising up. So what will be the pressure on the ground? Low pressure. Very good. Low pressure. Here the air is sinking down. It is falling down. So what do we have here? High pressure. Beautiful. So this gives us to the first conclusion which can be used uniformly across. That is, rising air parcel or air column always imposes a low pressure on the ground surface. Now, this rising air parcel can be because of temperature, can be because of other factors also. Sinking air always imposes a high pressure on the ground surface. But why will the air rise up? Why will the air sink down? Till now, are we comfortable? Up till this portion, are we comfortable? I don't want you after a class to tell me that what you taught yesterday, not anything has been understood. Good. Now, why is it that this air will rise up? Why will this air sink down? One of the conditions we have already studied, because of temperature. Warm air becomes lighter because of more energy the particles escape. Cold air becomes heavier, so you have basically more particles dominating it. So one of the factor is obviously going to be temperature. Yes, Ankush, it is a case of cold. This example is that of advection, cold advection. Now, temperature is one of the factors. But is temperature the only factor? The answer is no. For example, around 60-degree north and south latitude, 60-degree north, closer to the Arctic Circle we are talking about. So when you imagine that area, your natural perception in the mind is what? That it will be cold area. That region experiences a very significant low pressure, despite being a cold area. 30-degree north and south latitude, that is roughly around the region of all the desert areas in West Asia, etc., that you see, around to the slightly region around Delhi to the north of it. In that area, normal perception is that the temperature will be very high. That is a region of high pressure. So while temperature is one of the major factors which will always influence temperature, there are other factors at play as well. What is the other factor? And that brings us to the concept of thermal and dynamic pressure zones. So here, thermal and dynamic. Now, thermal we have already studied in very significantly greater detail, so I'm not going to spend much time on this. So here we will simply say that in the exertion of high or low pressure, due to factor of temperature. What does that mean? That means warmer regions tend to have low pressure. LP I am using wherever it is basically low pressure. Colder areas tend to have high pressure. We are comfortable up till this point, right? Now, the dynamic pressure. Dynamic in itself tells you what? Something which is mobile, something which is not fixed. So here, the creation and the creation of high and low pressure is because of wind movement, convergence and divergence of wind. What do we mean by convergence and divergence of wind? So for that, whichever room that you are sitting in or sleeping in or lying down covered under a blanket, whatever might be the condition, for a brief moment, take off the blanket and take a look at the room around you, whichever room that you are sitting in. Four walls, roof, floor, that's it. If the doors, windows, everything are closed, right? Let's think about if there is a wind movement in such a condition, in such a region, how will that wind movement happen? So let's consider this room. Let's go for a luxury room, a bigger one. Now here, let's observe the wind movement. So in the first scenario, assume that closer to the wherever in whichever room that you are sitting, let's assume closer to the floor, you have installed multiple different fans, the large fans that you see in the industrial kitchens, the hotels, etc., the large fans which give a lot of air. So from both sides of the floor, you have installed these fans, let's assume. here also, here also. Let's assume these fans are there, which are moving consistently, giving the air. Let's suppose here also, here also. Can you imagine a situation like this? I hope you can. Now, the winds will be pushed on the floor. Now, as the winds they come together, head to head, what will happen? Will it happen that one of them will go to the side and let the other move by? No, because the wind is consistently blowing from both sides. Can the wind dig a hole into the ground and simply go into the that I am tired of this, I want to gain solace, I will go to the center of earth itself? Will that be the case? No. Will that be the case that the wind will say that I have seen too much things in this room, now I cannot stay here, I need to disappear, so the winds will disappear all of a sudden? Will that happen? No. Where will the winds go? They have no other place to but to converge and eventually rise up, isn't it? They will have to converge and they will then rise up. Because more winds are coming along the way. So they will rise up here. So on the ground surface in this area, in this region, can we say that we have a rising air column? On the ground, can we say we have a rising air column? So let's suppose this is the ground surface. Here I have a rising air column. So what will be the pressure on the ground surface? Will the pressure increase or will the pressure decrease? If the air is rising up from here, the pressure on the ground surface, will it increase or will it decrease? Beautiful. It will decrease. Now, why has this pressure decreased? Is it because of temperature? We have not even discussed about the temperature of the wind till now. We have not discussed about the temperature of air in the room till now. We have simply discussed the fact that because of the situation that the winds had no other place to go, but they were forced to converge and eventually they were forced to rise up. So because of this, you have rising air column. Rising air column purely because of convergence of winds. And this convergence of winds leads to creation of a low pressure on the surface, regardless of the temperature near ground surface. Yes, Shreyas, that is true. In most of the cases, that is true. So that is basically the case of a low pressure created due to the convergence of wind. Now let's reverse this scenario. Let's think about the same room that you are sitting in, but this time we have installed the fans near the ceiling, the wall near the ceiling. We have installed the fans here. Let's suppose. And these fans are rotating. They are pushing air. Now this air is being pushed closer to the ceiling. Now, what will happen to this air? They will also converge. Consistently more air is coming along the way, so it cannot be the case that few of the some of the air particles they try to rest near the region of the ceiling, that let us spend some time here. No, more air is getting pushed. So the air, what will it do? Will it break through the ceiling that I want to look at the world? No, it cannot do that. It will eventually be pushed down. This air will eventually be pushed down. Now it will hit the ground surface. Air is going to hit the ground surface. It has been forced into convergence in the upper air. Now it is sinking and it is hitting the ground surface. So what will be the pressure on the ground surface? As it hits the ground surface, will the pressure increase or will the pressure decrease? Very good. The pressure will increase. And after this, where will the air go? The air eventually will be forced to move in either directions. In a way, there will be slight divergence. It will hit the ground and it will move in either directions. So here, you will observe a sinking air column. Sinking air column. And that sinking air column basically means a high pressure is created near the ground surface regardless of the temperature at the ground surface. Is that understood? Right? Is that okay? The fan, when it is installed in the middle of the ceiling, that carries out the normal convection movement, where generally that is why when you have the higher ceilinged rooms, where the ceiling is very high, the room tends to remain a bit cooler. Why? Because there you will have that convection which is allowed. The air rises up and the fan simply circulates the air to the sides, where the colder air is then pushed down and you have complete convection. Okay? So with this basic, we will move ahead and we will try to understand about the different types of wind movements. But before that, we'll take a break. So we take a break and we'll be back in around 15 minutes. We'll be back. Okay. A confirmation about the audio, please, guys. The audio is clear. Thank you. So now we move ahead. We have had some clue about what atmospheric pressure is. So we have seen from whatever things that we have studied till now that atmospheric pressure is the, in a lump sum manner, the weight imposed by the air particles on the ground surface. Now that weight can be variable, it can be increasing, it can be decreasing. So that weight is not always going to be consistent. So that brings us here to the concept of isobars. Isobars, they just like isotherms were imaginary lines joining places having similar temperature, isobars are the imaginary lines which end up joining the places exhibiting similar atmospheric pressure. So here when we talk about the isobars, here it is a line on a map connecting points having same atmospheric pressure at a given time or on an average over a given period. So let's suppose a region here has got A. It has got 1000 millibar of pressure. Let's suppose B, 1000 millibar of pressure. C, let's suppose 990 millibar. D, 1000 millibar. So here, the isobar which will basically be joining them will be demarcated as the 1000 millibar isobar. So it indicates also that all the places lying on this isobar will have a pressure, atmospheric pressure of around 1000 millibar. All the places which lie along this line will have this kind of an isobar. Okay. Now here, if you take a look at this image of the country, this is the isobaric representation. Here you would observe the various different isobars of different denomination. So let's suppose this is the 998 isobar. That means pressure on these areas, in almost all these areas, on an average are 998 millibar. Then 999 millibar pressure, right? Then 1000 millibar pressure. So in a way, they tell us about how the pressure is changing over a particular place, how that pressure is changing. The change of pressure from a high pressure point to a low pressure point, that change, that difference in pressure, that is what is known as pressure gradient. So when you talk about pressure gradient, it is a change in pressure with the horizontal distance. So when we say pressure gradient, is this portion of isobar understood, or is that isobar portion any doubt in that? On what basis are these imaginary lines derived from? Different places will have their own individual pressure, which are measured just like temperature is measured at the observing stations, pressure is also measured at observing stations. So different areas will have their own unique different pressure. So if you draw an imaginary line of equal pressure points, you get an isobar. Okay, Shreyas. So pressure gradient is the change in pressure, excuse me, change in pressure over a distance. That is high to low or low to high. So that is how the pressure generally changes. Now, over the same distance, or over any particular distance, how is it that the pressure is changing? right? If pressure changes rapidly over a small distance, we can say that the pressure gradient is high, or gradient of pressure is high. Of pressure is high. Now, if pressure changes very slowly, if there is a very small change in pressure over a distance, we can say pressure gradient of pressure is low. Now, why is this gradient of pressure important, if at all? Why is it that this gradient of pressure is important? We have seen that winds will blow from a high pressure to a low pressure, the region of excess to a region of deficiency, always. So if, let's suppose, the pressure is changing very rapidly, that means in a small distance, that high pressure is getting converted into a low pressure. Winds will move. If it is changing very slowly, winds will move slowly. Now, let us analyze this. Let us think about a distance. Let's suppose we consider a distance of around maybe 200 kilometers or 300 kilometers in this direction. This distance is actually more than around 1200 kilometers. So let's consider 1200 kilometers in this direction. Let's consider 1200 kilometers now in this direction. Let's suppose that these are equal distances. Let's assume this is the case A, this is the case B. By looking at isobars, where is it that we can conclude that pressure is changing more rapidly over the same distance? A or B? Beautiful. Why A? Rohit? So basically, from here, if we observe, the pressure here is 998 millibar. In both these cases, it is 998. By the time that you reach here, the pressure this side has become 1006. And here, it is less than 1000 millibar. So here, the pressure in that entire distance in A has varied by 2 millibar. And here in this region, it has varied by around 8 millibars. Here, there's a variation of 8 millibar. So there is a greater gradient or variation in pressure in the region of B as compared to A. Is that understood now? Dikshit, Rohit, Chetcha, all of you had said A. Is that clear now? That why in the region of B, we say that the pressure changes very rapidly, quite rapidly. So that variation in pressure over a distance, that is what is known as, that is what is regarded as the gradient of pressure. Okay. That is the gradient of pressure. So when we say pressure gradient, so the change in pressure with the horizontal distance is termed as pressure gradient. It gives an indication of how quickly or slowly the pressure is changing over a distance. So, we have remembered or we have discussed about the fact that high pressure is indicated by surplus or abundance of particles. Low pressure is indicated by vacancy or less particles. Wind motion will always be from a high pressure to a low pressure. Wind will always be in motion from a region of a high pressure to a region of low pressure. Observe here. This is the region of high pressure. Abundance of particles, air particles, vapor particles, dust particles, all of them, which exert their weight. Here you have the low pressure, means a deficiency in the availability of the air particles here. Isn't it? Very less number of particles are present here. So here you have abundant presence and here you have a kind of a deficiency. So excess particles will automatically initiate a motion like this. Now, can we say that the difference in quantity of high and low pressure will end up determining the wind motion also? For example, let me give you two instances. Case 1. Let's suppose high pressure is 1020 millibar. Low pressure is 990 millibar. Case 2. High pressure. High pressure indicates surplus of particles. Low pressure, how much vacancy is there? High pressure, let's suppose, is 1006 millibar. Low pressure is 998 millibar. So, in both these cases, will the wind motion be consistent? Will the wind motion be stronger in first case? Will the wind motion be stronger in the second case? Or we don't care about this question, we have better things to do in life. So choose out of these four what is the correct answer. Very good. The question, my dear friend, is what we are doing here. That is the biggest question. Very good. So here, basically, we can all agree to the fact that wind motion will be very, very strong in the first case because the high pressure is very high, low pressure is substantially low, just like in the case of flow of water. So when you pour water into, let's suppose from a jug, you are pouring water and you are taking a glass and you are pouring water, water will flow down. Why will the water fall down? because you are providing that height variation. You are providing that variation in height. Let's suppose you have taken the jug 1 meter higher up. Now, when the water will fall, the water will be falling with greater intensity, isn't it? Right? Because you have taken the jug higher up. Let's suppose you take this jug to the terrace, to the roof, and then you start pouring it. The velocity of water will keep on increasing, isn't it? But when you were closer to the glass of water, the velocity was less. So, in the case of water flow, what did we see? That greater the height difference, greater is the speed of flow. Similarly, in geomorphology also we had seen that a region which was having a significantly steeper gradient, steep slope, there the materials would move very fast as compared to a region which had a slope like this. Here the movement will be very small, right? Just like that, for the movement of air particles, wind is after all nothing but the movement of air particles. That is what we denote as wind. So when we talk about the movement of air particles, it is determined by what is the surplus and what is the deficiency. If there's a very significant difference between the surplus and the deficiency, as in this case, there's a very large difference in the high pressure and low pressure. So here, pressure gradient is very high. That is difference of pressure. Pressure gradient is very high. So automatically, air particles would initiate a motion. So you have a strong wind movement. In the second case, the gradient of pressure is very low. The difference between the high and the low pressure, that is very low. It is not an exaggerated difference, to say the least. So that is why there will be wind movement, but not as strong as is in the first case. Okay? Is that clear? Girish, is that understood? And Shruti, you also. I hope that is understood. Right? Okay. Now, after this, we move to the factors which influence the velocity and the direction of the wind, because in your day-to-day life also, it is not as if you have never experienced wind motion. You would have experienced it multiple times, hundreds of times, thousands of times. You step outside your house, most of the days you will find some or the other wind. It might not be that strong. It might be very weak, or it might be extraordinarily strong. So the velocity varies. We do know that. Velocity of the wind varies. Always, it is not that the wind is coming from the same direction. Sometimes the direction also changes. So there's a variation there also. If ever you have been to a taller building, let's suppose the 33rd floor, 19th, 13th floor onwards, if let's suppose you go to 20th floor, 19th floor, 31st floor, you would have observed that the wind motion there is much stronger as compared to when you were on the first or the second floor. So with height also the wind movement varies. So the wind actually that we observe, that we experience, is dependent on a host of many different factors, which end up influencing its speed, which ends up influencing its direction, and also in a vertical level also variation in speed is there. So other than the force of gravitation, the elephant in the room is always going to be present. So force of gravitation, few of you have had the misconception previously where you thought that when the wind will approach the mountain, it will take off and then will rest after reaching the sun. There we bust that myth by saying that wind will always be forced closer to the ground surface because of that force of gravity. So the force of gravity which acts downwards keeps the wind closer to the surface, keeps that horizontal movement of the wind. But when that wind is blowing, that wind in itself is driven by three different factors. What are those three factors? First factor is The pressure gradient force, the variation or the difference between the high and the low pressure. Another factor is the frictional force, the force of resistance offered by objects on the ground surface, buildings, trees, mountains, hills, everything, whichever they allow or they offer themselves as an obstruction. And then the Coriolis force, which bends the wind in the rightward direction in the northern hemisphere and in the leftward direction in the southern hemisphere. So let us understand each one of them, and then we will be able to formulate what are the permanent wind systems across the world. So first of all, the pressure gradient force. So the pressure gradient force, basically, whatever we have already seen, that their wind will always blow only from a high to a low. Regardless of whatever happens in your life, wind will never blow from a region of low pressure to a region of a high pressure. Wind will always blow from a region of a high pressure to the region of a low pressure. That is, from the region of, let's suppose, colder area where there is abundance of air particles to a region of vacancy where you have deficiency of particles or a low pressure. So high pressure to low pressure. Okay. Low pressure will attract winds. Simple basic thing in life. Now here, will all the winds be of same intensity? It cannot be. It cannot be the case that across the globe, all the winds are moving at the same speed. So it varies. The speed varies, the intensity varies. You would have seen sometimes there is slow breeze which comes and hits your face. Very pleasant. Sometimes there's such a strong wind that it picks up not only the dust particles, but maybe lighter pieces of materials also the wind carries off. So the speed is varying. On what factor? On the variation in between the high pressure and the low pressure. That is indicated by the gradient of pressure. So if the pressure gradient is high, wind speed will be high. If the pressure gradient is low, the wind speed generated will also be very, very low. So here, for example, you have the isobaric representation of the region of North America. Observe, you have the region of a high pressure, you have a region of a low pressure. So the ultimate direction of the wind or ultimate movement of wind has to happen from high pressure to low pressure. But will that be the case that this wind started at 15 kilometer per hour, maintained that speed of 15 kilometer per hour? It was a strong proponent of non-violence, maintained that proponent of 15 or speed of 15 kilometer per hour till its destination? No, wind speed will vary. So how can we decipher from here? What will be the speed of the wind? How the pressure is changing? That is the pressure gradient. Pressure gradient, what we have seen in the case of pressure gradient. Pressure gradient is the change in pressure with the horizontal distance. If the pressure is changing rapidly, means the gradient is high, means there will be strong wind. If the pressure is changing slowly, means the gradient is low. So for example, in this area, observe that the isobars are far away from each other. Isn't it? The isobars are very far away from each other. Means the pressure is changing very slowly here. The pressure is changing slowly. So the winds will be also moving very slow. Observe shallow gradient associated with weak winds. Why? Because the pressure is changing slowly. But come to here. Pressure in the same region, in that same distance, pressure is changing very rapidly. Each of the isobars represent new different pressure. So pressure is changing very rapidly. Means there's a steep gradient. Means the strong winds will be there. Right? So pressure gradient force and the existence of pressure gradient, that ends up determining the speed of movement of the wind. Okay? How quickly or how slowly the wind will move. Are we aware about the meaning of shallow and steep? It is not shallow. Are we aware about the meaning of shallow, Ankit? No. That is why that question arises. Shallow means open space. No. Have you heard about the term? These are the regions of shallow waters. These are the regions of deeper waters. Have you heard about this? No. Okay. Shallow means less, very less, right? People are also judged in the interview. Many of them are judged by the fact that this individual has got no depth in them. They are shallow, means they have superficial knowledge about things. They don't have a deeper understanding. So shallow means something which is very less. Steep means what? Steep, we have seen in geomorphology, this is steep, this is shallow gradient, this is steep gradient, means there is a sudden difference in height. That is what we call as steep. Steep means sudden. Steep demarcates a kind of a suddenness. Shallow demarcates a kind of a lesser portion. Okay. MB here refers to millibar. Is that understood? The meaning of steep and shallow now. Shallow gradient refers to very less gradient. Steep significant. This MB is millibar, guys. Why is this confusing you so much? Millibar. Basically, if I have to take you back, the average atmospheric pressure at sea level is 1013.2 millibar. Did you see this? Or did you guys simply ignore this? This is millibar. Millibar is a unit with which pressure is exerted, right? Just like temperature is basically indicated by degree Celsius. That is how millibar is also an indication of the pressure variation. Okay. 10 minus 1 is milli. Is it the case? Work on this, guys. Work on this. CSAT you have to clear. CSAT is something which, regardless of how much you study GS, CSAT you have to clear. Yes, deci, centi, milli. Come on. We cannot be studying about the portion of milli, centi, and deci at this point of time. Ritika, what is the last point which is not clear? High and low. Is that the pressure gradient? Ranjini, you have a question. Earth has gravity. The air moves to downwards. Why is it horizontal? The air moves from a region of high pressure to low pressure. The force of gravity, Ranjini, comes into play where it does not allow the air to simply, as it moves up the mountainous area, it does not allow the air to simply take off. The air will rather be fixated near the ground surface. That is where the gravitational pull come into existence. Okay. So here, Ritika, again focus here. The placement of isobars tell you that over this larger distance, the pressure is changing slowly. So we have seen earlier also that if the pressure change is very less, wind movement will be slower. If the pressure change is very significant, wind movement will be stronger. Here, over the smaller distance, the pressure change is very significant. That means there's a very significant gradient of pressure that will always indicate a very high wind movement. Now, we come to the second factor, which also influences the direction of the wind movement. It causes the bending of the wind. Now, that is the Coriolis force. Coriolis force basically is an apparent force which acts on any individual freely moving object, where objects moving in the northern hemisphere, because of the rotation of the earth, they bend to their right. Objects moving in the southern hemisphere, because of the rotation of the planet, they bend to their left. And this is all attributed from the same basic fact that we studied in module 1 itself. And in module 1, we had studied that when it comes to the speed of rotation, is the speed of rotation going to be similar across A, B, C, and D? Is the speed of rotation going to be similar? No. So out of A, B, C, and D, where is it that the speed of rotation is going to be highest? A. Very good. Why C? A is where the speed of rotation is going to be highest, because in one rotation, the region around equator will end up covering the largest distance, as we had studied in module 1 itself. Right? In one rotation, A will cover the largest distance. So speed of rotation is maximum of rotation varies from equator. Rotation of the planet I am talking about. Rotation varies from equator to the poles. As an object moves between places of different speeds, it suffers an apparent bending as the planet rotates. We'll see how it rotates. So basically, Coriolis force is an apparent force which acts on any rotating body, any rotating object, or rather not rotating object, any moving object in the northern or the southern hemisphere, if they are moving independent to the surface. And as they move, due to the rotation of the planet, the objects will end up getting deviated. So an apparent force exerted due to rotation of the planet. So if in an imaginary world, if you can imagine a planet which does not rotate, so in that case, no Coriolis force, okay, due to the rotation. Because it is because of the rotation of the planet that different areas have varying speeds, right? So here, the key to Coriolis effect is Earth's rotation. Specifically, Earth rotates faster at the equator than at the region of the poles. Why? Because Earth is widest at the equator. So to make one rotation in 24-hour period, equatorial regions move at around 1600 km per hour. Near the poles, the Earth rotates at almost 0.00008 kilometer per hour, or almost around, roughly, if you can think about it, 8 centimeter or less than that per hour. So there, the speed of rotation is almost zero at the poles. It is maximum at the equator. So any object moving in the northern hemisphere bends to its right. Any object moving in the southern hemisphere bends to its left. Objects moving in the northern hemisphere bend to the right. Objects moving in southern hemisphere bend to the left. Yes, Nikat, that is correct. Now, why does this happen? Why will it not bend to the left in the northern hemisphere? Why not to the right in the southern hemisphere? Is it something decided by God? So the answer is no. So here, let us understand the logic. By the way, let me tell you, even for the simpletons or even for the generalistic approach for GS, nobody is going to ask you the reason. Even this much information is more than sufficient. Okay, you don't necessarily have to go into the deep and understand the reasons. Even this much level of understanding that Coriolis force is a force because of the rotation of planet Earth, because different areas have different rotational speeds. So object in the northern hemisphere will bend to the right, objects in the southern hemisphere will bend to the left. This much understanding is more than sufficient for the requirement of GS. But in case you want to look into it, why? So let us understand that. Let us consider different cases of the car example. So let's assume the first case. When two cars they are moving let's suppose the first one is moving at a speed of 140 kilometer per hour. The second one is moving at a speed of 10 kilometer per hour. Let's assume. Now, an individual from the first car, let's name this car A, let's name this car B. An individual from car A throws a ball. Now, will that ball be caught by the person in car B? Will that ball fall ahead of car B? Or will that ball fall behind car B? What do you think? What will be the case in this one? Think about it again. One is moving at a speed of, A is moving at a speed of 140 kilometer per hour. B is moving at a speed of 10 kilometer per hour. Now A has thrown a ball, right? Will that ball, so think about yourself traveling. Most of you would be doing that kind of a thing, unwanted thing on the roads where you move at a very high speed. You throw something. Now, where that does that object go? Does that object also have a forward motion? Does that object start moving backward? Or does that object stay where it is, where you have thrown there itself, it stays? So what is the, so in this case, will that ball fall ahead of car B? Will it be caught by the person in car B, or will it fall behind car B? Okay, clearly very confused. So let me give you another instance. Let's suppose you have two cars. One is moving at 40 km per hour. Another is also moving at 40 km per hour. A, B. Now, if a ball is thrown from A, will it fall ahead of B? Will it fall behind B? Or will it be caught by the person who is sitting in B? Very good. What is equidistant? Equidistant from whom? Okay. So you would have seen this basically. If ever you have not seen this, you would have definitely done this in your life, but clearly the attention would have been somewhere else. If you have two motorbikes moving at the same speed, you can almost hold a conversation between each other, isn't it? You can basically hand out stuff from from one vehicle to the other person will be able to get your stuff. Why is it so? Even if both of you are moving at 80 kilometer per hour or 100 kilometer per hour, you'll be able to exchange items. Why? Because with respect to each other, you are moving at same speed, right? So with respect to each other, you are almost static, right? So here, when an individual basically throws a ball here, that will be caught by the person in B, right? Now, the third scenario basically is if two objects are moving again, A, B. Now, A is moving at a speed of 10 kilometer per hour or 20 kilometer per hour, let's suppose. B is moving at a speed of 160 kilometer per hour. Now, a person from A throws a ball. Now, will that ball be caught by the person sitting in B? Will that ball fall ahead in this region of B? Or will that ball fall behind B? What do you think? We can all agree, other than one of you, all of you have given the same answer. So one of you have given the incorrect answer, but rest all of you have given the same answer. That is, by the time that the ball will reach here, B would have reached somewhere here maybe because B is moving at a faster speed, right? So from a layman's perspective, if you ask that layman person that A had thrown a ball, where did the ball go? So the answer would be the ball fell behind B because by the time that the ball could reach there, B had already moved ahead. So here, if an object moves from slower speed to faster speed, it falls behind. We can have the conclusion. We can have this as a conclusion. Another conclusion we can have is if an object moves in between similar speeds, there is no deviation. We can have this conclusion also. Now, in this case, the first case, now tell me, as from a person throws a ball towards B. A is moving at 140 km per hour. B is moving at a miserly 10 km per hour. So, will the ball fall behind B, be caught by B, or will fall ahead? Ahead, right? Good. So, here, if an object moves from a faster speed to a slower speed, it falls ahead. So let me name this my first conclusion. Let me name this my second conclusion. And let me name this as my third conclusion. Are we comfortable up till here? Till now, we have not been talking about the planet. We will implement it now. But are we comfortable up till here? I was waiting. I was waiting for the intelligent people to take over. Very nice. But we are assuming there is no force of wind in this case. If the car moves very fast, usually the wind moves backward, taking the object with it. Hmm. That is why sometimes I like that intellectual kind of a thing. Hmm. So when the car is moving very fast, does that wind start blowing all across the planet because someone in Delhi is moving a car very fast? Or is that going to be a very localized phenomena restricted only into the region of the car? When you are throwing the ball, will you provide some momentum to the ball, or simply you dangle the ball outside and you let the air take care of it? If you simply dangle the ball outside, then even in the second scenario, you can never make the ball reach the other car. So the very proposition that the ball is reaching the other car means you have got a significant amount of impetus that you have provided, a significant amount of momentum by the factor of impulse. You have provided that impulse and momentum, due to which the ball is able to overcome that drag of the wind, the frictional drag of the wind. Only then will is it able, because think about it, 40 km per hour is not a small speed, is it? Still, here you will experience the wind motion. So if you are throwing the ball, we are assuming that the impetus that you are providing to the ball, the momentum of the ball, is always going to exceed that. So here also, as the car goes with a significantly greater speed, there will be wind, but your momentum that you have provided is enough to overcome that. Is that now understood? Yes? Okay. And the ball has air in it too, so it's hard to wind to drag the ball. Okay. I won't go into, see, you guys are much better scientists than I can ever be, so I won't entertain these thoughts. Always object will fall behind, not respect to anything but respect to the surrounding. A deeper thought, very deep. Good. So the crux of it all, have we understood the portion that we have discussed till now? Understood? Right? Okay, good. Now, let us implement all of this across planet Earth. Now, let us think, first of all, about the region of equator. Or let me draw equator by a darker shade here. Let's suppose this is your equator. Let's suppose this is around 40 degrees. Let's suppose this is around whatever. Here also, let's assume 40 degrees. And just for the sake of it, because variety in life is also very important, so let's draw these 5-degree north and south of equator. Now, here, let's assume these are 5-degree north, 5-degree south. Now, let's have different places. A, B, C. An object is trying to move from B to A. Let's suppose. An object, okay, I have not placed A, B vertically here. Let's place this in a straight manner. Let's suppose this is A. An object is trying to move from B to A. So, these places will be rotating at different speeds. B is rotating slower, A is rotating faster. Can we say this is the case of an object moving from a slower speed to a faster speed? Comfortable up till here? Can we say that this is a case of an object moving between a slower speed to a region of a faster speed? What happens? When an object moves from a slower speed to a faster speed, it falls behind, isn't it? Implement that. So, by the time that the object will reach the place around A, the A rotates so very fast, it will move somewhere ahead. So here, it will fall somewhere behind. Maybe at a region we know as A dash. Okay, it has fallen behind. So this is what kind of a bend? This is a bend in the right direction, rightward direction. Always, when you observe that bend, you observe the region of the origin. From the zone of origin, it is a rightward direction. Similarly, if we talk about an object moving from A to B, object is trying to move from A to B. Now, this is clearly a case of moving from faster speed to a slower speed because B is rotating at a faster speed. B is rotating at a slower speed. A is moving at a faster speed. So what happens in that case? If an object moves from a faster speed to a slower speed, it falls ahead. So here, it will fall ahead of B. B dash. What kind of a bend is this? It is a rightward bend. Now let's talk about the southern hemisphere. In the southern hemisphere, let's suppose the object is moving from A to C. So again, it is going to move from a faster speed to a slower speed. C is moving slowly. So as a result of that, it will fall ahead. Somewhere here, C dash. What is this bend? It is a leftward bend. The movement is happening and is bending in a leftward direction. Now let's suppose from C to A. Object has been moving from C. It is trying to move towards A. But A is moving at a much faster speed. So this will be falling behind. This will fall somewhere, let's suppose here. A double dash. Isn't it? What is this bend? It is in leftward direction. That is why objects moving in northern hemisphere, whenever they are moving either towards equator, away from equator, they will be indicating a rightward deviation. Objects moving in the leftward or in the southern hemisphere will indicate a leftward deviation. Okay, that is why even the airplanes that you fly, these airplanes, their routes, they basically account for this Coriolis force. So let's suppose an airplane moving from Delhi to Bangalore. Bangalore is closer to the equator. So let's suppose Delhi to Bangalore. Ideally, let's suppose. So this plane will experience a rightward bend because the region near equator will be moving ahead. So that is why if they would have taken a straight path here, they would have rather ended up somewhere behind Bangalore, maybe in Mysore. That is why they adjust their flight paths in such a manner. You will observe, I'm not talking about the traffic adjustment, only due to Coriolis force. So you will observe generally they will fly like this, account for the bend, and then they will land here. Okay. Ocean currents also indicate a bend owing to the Coriolis force. The missiles that you launch, you have to factor in the Coriolis bend as well. In fact, in some of the sniper schools also, the snipers are the people who basically have the, I hope you are aware about the sniper shots, the sniper rifles, which can shoot for 4 kilometers, 5 kilometers into the distance. They also account for the slight Coriolis force. So Coriolis bending is because of the rotation of the planet. Having said that, around the region of 5 degree north, 5 degree south, now, this is the zone very close to equator, very, very close to equator. So here, let's suppose I name a place as 1. I name this place as 2. Now, can I say, can I come to this conclusion that the speed of rotation around 1 and 2 will be almost similar? Because that is the region around equator where the speed is maximum. So 5 degree north, 5 degree south, we can basically say that the speed of rotation is almost similar. So if the speed is similar, if an object moves between similar speed, what do we see? Between similar speed, there is no deviation. That is why around the region of equator, there will be no bending whatsoever, no deviation whatsoever, because the speed of rotation is similar. Now, till now, whatever we have discussed that there is going to be a deviation, a bending, because of, in a way, can I simplify that because of the difference in relative velocities of different places, there is going to be bending? If all the places would have been moving at the same velocity, let's suppose, then we would not have had any bending, any deviation. There is that difference in velocities in different places. So relative velocity, wherever it is different, there will be bending. Can we come to that conclusion? Can that bring me to another conclusion? That greater the difference of velocities in different places, greater will be the bend also. Can we come to that conclusion also? That greater the difference in velocities in different places, there will be greater bending. Now, let me take the example of the poles here. P. Speed is equal to 0. Right? So whatever might be the speed of rotation here at D, the difference or the speed of rotation at D, whatever might that be the case, will always be very great than speed of rotation at P, because speed of rotation at P is 0. Even if it is 15 kilometer per hour, 20 kilometer per hour, 30 kilometer per hour, there will be a significant difference in speed, isn't it? Because P is rotating at 0 here. So there you will always have a greater difference in velocities. So the bending will also be very, very high. Okay, so that is the factor of the Coriolis force. Now, when we talk about the winds, winds will always blow from a high to a low, always. Pressure gradient force basically carries the wind from a high pressure to a low pressure. So let's suppose if I talk about the northern hemisphere, and if I have the high pressure here, low pressure here, can I say that the direction of the pressure gradient force is like this? Can I say this? Perfect? No issues in this? Yes? But will the wind move in that manner? The wind will be impacted by the Coriolis force. Because we are in northern hemisphere, the wind will try to bend this movement in the rightward direction. This will be the direction of the Coriolis force. It will try to bend in the rightward direction. Eventual resultant of movement of the wind will be somewhat like this. This is your resultant movement. This is the direction of your pressure gradient force. Right? Now, let's suppose we are talking about the southern hemisphere. So here, let's suppose you have the high pressure. Let's suppose you have the low pressure. So the direction of the pressure gradient force will be, this will be the direction of the pressure gradient force, isn't it? But we are in the southern hemisphere. So because we are in the southern hemisphere, the winds will try to deviate to the left because of the Coriolis force. What will be the direction of the Coriolis force? This will be the direction of the Coriolis force. Eventual wind movement will be, the resultant movement will be the mean of these two. Right? Comfortable up till this point? Any doubts up till this point? Comfortable. Okay. When the air would move from B to C, there would be no deviation. Very good question, Kushi. When the, and if, first of all, when, more than when, if the wind does move from B to C, initially it will bend to the rightward direction like this. After crossing the equator, it will start bending in the leftward direction. So that will be the motion. Around the region of equator, no deviation. But if, let's suppose, it has to reach C, it will start bending in the leftward direction. So there will be two such bending. Okay? Good question. That will be put to use when we study the portion of Indian monsoons. Now, then we come to the portion of Coriolis force. So Coriolis force deflects the wind to the right direction in the northern hemisphere and to the left in the southern hemisphere. Even this simple idea is more than sufficient. Deflection is more when the wind velocity is also high. It is maximum. The deflection is maximum at the poles and is absent at equator. The Coriolis force acts perpendicular to the pressure gradient force. This is the direction of the pressure gradient force. This is the direction of the pressure gradient force. Coriolis force acts perpendicular to it. Okay? Now, then comes the next important force, that is the force of friction. Frictional force, you would all have basically experienced this or read this somewhere. It is simply the force of resistance. So if we talk about, let's suppose, the land surface, any land area, let's suppose any region of land. Okay. Let's suppose here you have a hillock also, a kind of a mountainous hill region also. Now, if I ask you that where is it that the wind velocity will be more? At this portion 1 or at this region 2? Where is it that the wind velocity will be more? 1 or 2? Always 2. Why? Because in the region of 1, the wind will face many resistances, many different objects in the pathway of motion. Trees, buildings, forests, mountains, plateaus, hillocks, everything. They will reduce the velocity of the wind. Right? So frictional force reduces the wind velocity. That is why as you move higher up, the winds, they start moving faster and much faster. Okay? Now, if from this, if I ask you, let's suppose this is the land area, and let's suppose this is the water body, the sea. Now, over the sea, wind motion will be faster or slower? Over the sea, wind motion will be very fast. Very good. Because over the water body, there is no such resistance offered in the form of trees, mountains, etc. It is almost smoother. So that is why near the sea surface, the wind is always very fast. That is why when you go to the coastal areas, you will always experience very, very fast movement of the winds. Right? Having said that, now if I ask you the question, out of northern hemisphere in comparison to the southern hemisphere, out of both these hemispheres, where is it that the wind speed in general will be higher? Northern hemisphere or the southern hemisphere? Very good. Always southern hemisphere in general. There the wind speed is much higher. Why? Because of dominance of water bodies in the southern hemisphere. Right? For example, you have, we will study very soon that in between the 30 to 60 degrees, you have the movement of wind in the form of westerlies. Westerlies in the northern hemisphere, yes, they can bring rainfall, they can sometimes bring storms also. But in the southern hemisphere, the westerlies are given names because of the sound that they make. You would have heard basically when the wind moves very strongly, you have a kind of a harrowing sound associated, isn't it? That is why westerlies, where they blow in the region of the Southern Ocean, they are associated, they are given with different names. They are known by the furious 40s, the shrieking 60s. 40s, 60s, and 50s here refers to the latitude. So the furious 40s, the shrieking 60s, that is the name associated with the westerlies. The fiery 50s, why? Because they emanate that sound. That is why for a long period of time, until we had much stronger ships which came into existence, even moving to Antarctica would be a nightmare. Only few ships in the world would be able to withstand that journey because the winds, they become so very fast. And when the winds become strong, they are able to generate large waves. And that becomes a nightmare for navigation. But nonetheless, that is about the force of friction. Okay? In Coriolis force, the bending of northern and southern is from equator, not always. If an object has to move from B to D, this will also bend to the right. From D to B, this will also bend to the right. So wherever they will move, they will bend. How Coriolis force is perpendicular to the pressure gradient force. What is the direction of pressure gradient force? From high pressure to low pressure. Coriolis force will try to bend it to the left or right. So will it be perpendicular to the pressure gradient force or not? Okay. Then, after that, we come to the concept of the onshore and offshore winds. What are these? What are onshore winds and what do we mean by offshore winds? So basically, when you have winds which move onshore, onto the shore, shore is the coastline. So when the winds, they come from water to the land areas, let's suppose the wind motion is like this. Now these are your onshore winds. Movement of winds from water to the land. Now, let me know one thing. Will this wind bring moisture along with it, or will this wind be very dry in nature? What do you think? The onshore wind. It will bring a lot of moisture because it is coming from over the water body. It will drag a lot of vapor, lot of moisture. That is when cloud formation is accelerated. So onshore winds are always associated with heavy rains. Always bring rains. That is why you will find that those regions which are in the interior, where no such winds can reach from the water body, no such winds can ever possibly reach these areas carrying moisture because moisture will be dropped along the way. These regions are very dry, desertified almost. Okay, offshore. So let's suppose if there is a wind movement like this from land to the sea, movement of winds from land to the sea. That is offshore winds. Now, these winds which are coming over from the land surface and then moving over to the water body, before entering the water body, will they be dry or will they be moist? What do you think? They will be dry. Very good. They will be dry because from land areas, they don't get any source of moisture. That is why these are associated with dry winds which don't bring rain. Okay, so that is the case of onshore and offshore wind movement. Now, across the world, the presence of onshore and offshore winds, as you will see later on as well, plays a very, very important factor in the causation of rainfall. This is the reason why I have been telling you since the time of geomorphology and continental drift itself, if you recall it by now, we have talked about the fact that in the time of Pangaea, majority of Pangaea was a desert. Majority of Pangaea was a desert. It was only around the fringes of Pangaea that few regions received some amount of rainfall. And in these conditions of very dry conditions, reptiles could survive, mammals could not. That is where when you study, or if you study about the evolution of species, you'll find that during the time of the Pangaea, the lizards, they thrived. The reptiles, the reptilian population, they thrived. And that is how eventually you had the dinosaurs, which evolved. Obviously, when the basic continents they separated, rainfall could then be observed in various different areas also. So the presence of onshore and offshore winds, if they are that very important, and we do know that the land masses have not always been consistently present in the same area. So at one point of time, you could have the Indian subcontinent present in this region. The region of Rajasthan was not always a desert. Africa at one point of time was further southwards. Sahara was not always a desert. In fact, Sahara was a dense forested area as recently as 14,000 years back. It is when, in whichever position you are, whether you are experiencing onshore winds, rainfall, offshore winds, lack of rainfall. As we speak, as of now, winds over India, they are offshore. They are moving from land into the region of Arabian Sea and Bay of Bengal. That is why we are not receiving that much amount of rainfall. During the summer season, the winds become onshore and we experience the monsoons. That is the broader outcome of it. Okay. Now, then we come to the air circulation. Why is it that the circulation of air happens? So basically, always the traders, the sailors, the mariners, they always reported that there is a movement, consistent movement of the wind. After all, they would use those winds to reach from place A to place B. So that is why they were always sure that there is an air circulation which happens. But why does it happen? That is because of the simple factor that different places they get heated at a different rate because of variation in the amount of solar insolation. We do know rate of heating is different in different regions. Now, we do know that temperature influences the pressure, induces a difference of pressure in various places. As it induces a difference of pressure, induces a movement of the wind. And we also know that when the wind moves, it is a complete circulation which happens. It is not only from the ground surface the wind will move, upper air will take care of itself. It is because of this particular understanding of different places having different temperature that Hadley basically arrived at a model of circulation that was referred to as the unicellular model of atmospheric circulation. Model of circulation. Now, why it was named unicellular? Because the concept was very simple. The concept was that, look, around the region of equator or 0 degree, and then we consider 90-degree north, we consider 90-degree south. And his concept was that around the region of equator or 0 degree, the air will get heated up because the land gets heated up. So the air will also get heated up. The air, after getting heated up, will rise. Will rise up till where? Will rise up till tropopause. It will rise up till tropopause. That is when the air will diverge. The air will diverge. And around the region of the poles, you have the colder conditions. Remember the circulation that we studied here. If I can take your memory back here, this circulation from the warmer area to the colder area, there is a continuous circulation of air. If you recall the similar kind of a movement, that is what Hadley arrived at, that there is a kind of a similar motion here. Across the entirety of the planet, there is a kind of a similar motion. So he said that warm air around the region of equator will get heated up, will rise up, creating a vacancy near the ground surface. That warm air will hit the region of tropopause. It will diverge. It will move towards both the poles. It will sink and then will converge together. So that is basically, in each of the hemispheres, you had the formation of one cell of circulation. Hence the name unicellular model of circulation. For a long period of time, this was believed because this was purely a thermal model. That is, the pressure systems which are influenced only by temperature. And you did not have a greater understanding of science. Era of discovery had not set in. But the sailors, the mariners, the merchants, and the traders, they started reporting something else. They said that, look, it, if this model is to be followed, that means on the surface, there is movement of winds continuously from the region of equator to from the region of the poles to the region of equator. So the wind should always be moving in the same direction, but they are not. They found the movement of wind toward from equator to the poles also. So why is that happening? And also, it was understood that no wind will be so powerful enough, no wind can be so powerful enough that it initiates its journey from the region of the poles and it reaches all the way to the region of equator. It simply cannot happen under no circumstance, because the frictional force will weaken the wind along the way. It won't be able to reach tens of thousands of kilometers in the same distance. And we got to know about another major factor, and that is the Coriolis force. The Coriolis force's bending would never have allowed the wind to reach as far as the equator. It would have bent in this region itself. So that is why this model was eventually discarded. It was William Ferrel who observed this Coriolis force bending and various different types of pressure developed in between. That is when he postulated what is known as the tricellular model of atmospheric circulation, which we shall be studying tomorrow. Okay, so that is where we restrict the session here for today. We initiate the discussion from tricellular model of circulation tomorrow. Above sea, there is foggy environment. Is it going to affect the wind speed? See, the formation of fog in itself is determined by the wind movement. If there is a wind movement, there will never be a fog formation. Right, fog formation will happen only in certain areas, but in the region of the fog, if there's a wind movement, it will drag the fog away. So it is always codependent on each other. By the time that we come to it, fog in itself will not alter the speed of the wind, if that is the question that you're asking. Do we need to learn the name of the scientist who discovered what? A slight idea about them will always enrich your answer. Likhani, was there no onshore winds on Panja? There was, but it was restricted into the mountainous areas closer to the coastline. The inland areas were significantly denied the movement of onshore winds. That because of the obstruction of land. That is why you had dry conditions. Okay, so that is where we'll restrict the session. We meet again tomorrow, where we carry the discussion forward. Till that point of time, take care of yourself. Goodbye. Thank you and good night.